It's that time of year again, the time of cold nights, warm fires, and Christmas specials. With the temperature dropping, however, it's important for us to maintain our body temperature to prevent any colds from happening. Most people in the South typically just use warmer clothing to bundle up, but the people in the North face harsher, more severe, low temperatures that clothing cannot always keep out. This is where chemical heat packs come into play to keep you warm and toasty over the holidays.
Chemical heat packs are used for many different reasons. The most common use, as Miles said, is to keep warm with hand and feet warmers. They can also be used for athletes in sports. The heat packs are used to release tension and straining in muscles to loosen them so the athlete can continue playing. The difference between these various purposes is the design of the heat packs. The hand and feet warmers are much smaller and more comfortable. They are built to fit into gloves and into shoes because they are farther from the heart and therefore don't receive as much heat from the body. So these are very beneficial to those body parts. They also allow for activities such as snow skiing and snowboarding without any interference and staying warm while still enjoying the outdoors. The sport heat packs are more flexible and larger to cover a wider surface area of the entire muscle. They can also be adhesive or sticky so that the athlete can play with it still attached to continue the relief. Though they serve a different purpose, they are very similar in chemical function. The reactants of chemical heat packs are oxygen and iron 3. The product is the iron oxide. The equation should look something like this.
The iron is contained inside the packet or strip of a thin fabric to allow oxygen in. The oxygen enters the heat pack when the packaging is open, which immediately triggers the reaction to begin. The oxygen oxidizes the iron and creates an exothermic reaction because the heat energy is released from the pack. Therefore, the packaging must be airtight to prevent any oxygen from entering and starting the reaction before the consumer is ready to use it. This could cause some problems with transportation if the packaging is damaged at all on the delivery to the marketplace. Another way to tell that the reaction is exothermic is because the change in enthalpy is negative. Using the heat of formation, you can calculate it. Both the elements, iron and oxygen, have 0 kilojoules because they are pure elements. The product Fe2O3, which is iron oxide, has a heat of formation of negative 826 kilojoules moles. From school sites, schoolworld.com. The equation to find enthalpy is the change in H is the enthalpy of the products minus enthalpy of the reactions. Then you plug in the numbers that I just went over with the coefficients incorporated to include the moles, so 2, 3, and 4. This will result in an enthalpy of negative 1,652 kilojoules moles of Fe2O3.
Now that you have the equation, you can even draw the Lewis structure for the reaction. It will probably look something like this. Now that you have the basics down, we can go into more detail with the heat packs and all the chemistry between the little packet of heat in your hand.
Let's start by looking at the surface area of the human hand. The area is the length times the width for the palm and the, Alrighty, now the measurements we measured on Gracie's hand is equal to 2.95 inches in length and 3.1 inches in width, which is equal to 9.15 inches squared, which we converted into 23.24 centimeters squared by multiplying the inch by 2.54 centimeters. The depth of the hand is 4 millimeters deep. This was also converted into 0.4 centimeters. The overall volume of the skin of your palm of your hand is 23.24 centimeters squared times 0.4 centimeters is equal to 9.29 centimeters cubed. Now, because density is meters over volume, you can use the volume of skin, 9.29 centimeters cubed, and density of skin, which is 1,050 kilojoules per mole, to find the mass, which is 9.75 grams. You then plug this into the equation, Q equals Cs, which is the specific heat capacity, times the grams, times the change in T, with the specific heat capacity for your skin, which is 3.47 degrees Celsius for specific heat of skin. and plus 4 degrees Celsius for the change in temperature. So the final equation should look like this.
Crazy calculations, I know, but it just goes to show how complex these small devices are. Just something that fits in the palm of your hand can give off so much heat energy. There are some different types of heat packs, of course, for different purposes, like the athletic heat sticker. They're also made of silica gel that's heated and cooled using the microwave and freezer. These are reusable, but for more extreme climates and adventures. And then there's the rice/wheat packs used in Canada. These are boiled and can actually be dangerous with flammability. Though the iron heat packs are a one-time use, they prove to be all around the best with their steady, comfortable heat release. Just watch the warning label that claims that they can get overheated. Dispose of when this happens, and then keep away from infants. Also, ingesting iron would not be a smart idea, but other than those warnings, use with caution and enjoy the holidays toasty and cozy.